Hey everybody, let's go ahead and start Unit 1B. Today we're going to be extending our understanding of end behavior, but this time we're going to be talking about rational functions. Remember, the root word of rational functions is ratio, which means a rational function looks kind of like a fraction, this idea of a ratio. So the ratio of two polynomials where the polynomial cannot equal 0 is a rational function. And remember, we say g of x cannot equal 0 because then it would be undefined. All right, so let's go ahead and talk about this. So if I'm talking about a domain of a rational function, so this is our graph here. This is our example 1 graph. This is what it looks like. Remember that our domain describes what the x can be. Another way of describing what x can't be is to know what x also cannot be. And when we're talking about domain within rational functions, we know that there's this red flag of that the denominator cannot equal to 0. So we set the denominator 3x plus 12, and we're going to set it equal to 0 so that we know what we don't want it to be. So we're going to subtract 12 to both sides. We get 3x equals negative 12. Divide both sides by 3. So we know, hey, if x equals negative 4, that's going to make our denominator a 0, which is a problem for us. So we actually do not want x to equal negative 4. So how do we, and we can kind of see that here, right here, where x equals negative 4. We can kind of see here, here's negative 1, 2, 3, 4. So how do I show what x can be? So remember, if I was talking about like x on our number line, if this was negative 4, x can be every other number except for negative 4 and then after. So how do we describe this? Well, we say it's from negative infinity up to negative 4, doesn't include it, and again after 4, really close to 4, and then to infinity. So how do we find the domain of other rational functions? So again, when we're talking about the domain, we're only talking about what would make the denominator equal to 0. So let's go ahead and set the denominator equal to 0, just like we've been doing. We know how to solve this. We're going to factor what multiplies to negative 24 and adds to negative 2. That looks like negative 6 and positive 4. So we end up with x minus 6 times x plus 4 equals to 0. This gives me zeros of 6 and negative 4. But remember, do I want a 0 in the denominator? No. So we actually say x cannot equal 6 or 4. If I were to sketch this on a number line, here's negative 4, here's 6. I want the domain can be any number up to 4, in between negative 4 and 6, and after 6. So how do we write this interval? Well, we say here it's from negative infinity to negative 4, doesn't include it. Again, from 4 to 6, negative 4 to 6, I should say. And then again from 6 to positive infinity. And of course, we put those unions in between. How do we find the domain of a graph if I don't actually know what the full polynomial is? Well, I can see here that there are some definite indicators of where we can't have some value. So where we see some vertical asymptotes, we see them here, they're invisible, but you can draw them in where we know we have kind of like a guide, a boundary where the function isn't crossing. So we see here where x equals, let's count. Here's 1, 2, 3, 4, 5. So at x equals 5, we have an asymptote, so we say x cannot equal 5. And here at negative 2, so at x is negative 2 also cannot work. So how do we describe that domain? Well, we can say, hey, x can be any number from negative infinity up to this negative 2 value, and then from negative 2 to 5, and then again from 5 to infinity. So we say from negative infinity to negative 2, and then from negative 2 to 5, and then from 5 to infinity. Okay, so let's talk about what end behavior of rational functions can be. So we're just going to look at what the graph is doing right now. So here's our graph right here. So we can see, just like as we would talk about the left side. So let's talk about the left side. So the limit as x approaches negative infinity is how we say the left, right? So as we go to the left, what is happening to our function? Our function, you can see, is slowly starting to go down, 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 down. So as we go to the left, the function is going downward. So we say the function, which is f of x, is going to negative infinity. And for the right side here, or as the limit as x approaches infinity, f of x is going where? Well, we can see this is going to go up, 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 up. So we say that's to positive infinity. Okay, so looking at the next example, let's look to see what's the end behavior following these rational functions. So again, I don't know what this number 5 looks like. I just have its function. So we're going to use our graphing calculator. Make sure that you go ahead and take that out right now. This is super important. Okay, in order to show this in my graphing calculator, I'm going to show you what this looks like. Here we go. Here's our graphing calculator. All right, so we're going to go to our y equals, and we're going to type in what our function looks like. So remember, a numerator is going to be separate. So you're going to put parentheses around the numerator. So parentheses, whoops, hold on. I have to zoom back in, sorry. Here we go. So we're going to go parentheses 4x minus 1, close parentheses, and then we're going to divide by to get that bar, and then we're going to put another parentheses around the denominator. So parentheses x squared minus 2x minus 24. Once we have that all typed in, you're going to hit graph. So we can kind of see what our graph looks like here, okay? So I like to give myself a little kind of sketch about what the graph is doing. Here's my little sketch, and we're going to look something like this. Okay, just give yourself a little sketch so you can kind of see what's happening here. Okay, so once I have that, I'm also going to see, okay, as x is going really, really to the left. So I see that here. As we're going to the left, what's happening to the overall function? As we're going to the right, what's happening to the overall function? So as we go to the left, we can say, you know, x is 10, x is 100, x is 1,000, x is to 10,000. So let's plug that in. So instead of hitting table, where you have to scroll down, we're going to go to second and then table set, which is your window. So I'm going to write that here. You're going to go to second and then click the window key, which is the table set. And what you're going to do here is we're going to say ask on that independent x value. So that way it'll ask you what values you want to plug in, and then you don't have to scroll through. So once you hit ask, go back to your table. So second graph to find your table. There's nothing there because we haven't told it what we want it to find yet. So let's plug in this first value here of 10. Okay, so we're plugging in 10. And we get 0.6964. Let's plug in 100, and we get 0.0408. Let's plug in 1,000. Whoops, forgot the 1. And we get 0.004. What do we notice about these values of y as we go through? So 0.69, 0.04, 0.004. It's getting smaller and smaller and smaller. And if I plug in the last one, 10,000, we get super, super small, right? E to the negative 4 is like saying 4 times 10 to the negative 4 power. That's like saying 0.0004. So it's getting smaller and smaller and smaller. And this is approaching almost 0. So as I'm looking here on this graph, as it gets closer and closer and closer and closer, that we're approaching that 0 value. It's never going to cross that 0 value. So we say that the limit as x approaches negative infinity, right, it's going to the left, that g of x is approaching 0 or getting closer and closer and closer to 0. Let's see what's happening if I start looking at the, oh, sorry, that was the positive side. It's the same idea though. As we get closer and closer and closer to 0, it's also 0. So let's look at the next one. Let's look at negative 10. We get negative 0.427, negative 100 is, oops, sorry, forgot the negative. Let's plug it in. Negative 100 is negative 0.039. Negative 1,000, we get negative 0.004. And then negative 10,000. We get negative 4 times 10 to the negative 4 power was like saying negative 0.0004. Okay, so again, we're going to the left and we're getting closer and closer and closer to 0 from the bottom. So we say the limit as x approaches positive infinity going to the right, g of x is also approaching 0. So that's how you would use your calculator to look at that. If you want to go back and look at this, you can see it just like that. All right, let's look at the next example, number 6. This is already graphed for us. So we're looking at a couple of things. So now as we're looking for what's happening on the right and left-hand behaviors, remember this is here and that's my right and this is my left, okay? I'm noticing something overall about my function is so that there's this like gap in between this and this here. And that gap is because there's this invisible horizontal asymptote here. So let's go ahead and kind of sketch that in where we know it's getting really, really close to this value at y equals -2. Really, 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 really close to it. And as we get closer and closer and closer, it's going to go towards that -2 and it's going to go towards that -2 but never ever touch it. So we say, hey, on the left side, the limit as x approaches -infinity, f of x is getting really, really, really close to -2 for that y value. And the same thing on the right side. The limit as x approaches positive infinity, f of x is going to be approaching or that equal to that -2 value. And the last thing that we need to talk about, horizontal asymptote, so that's a boundary. The line y, so if I sketch this, okay, if I were to say there's a horizontal asymptote, well, I should probably put it in, there's like this horizontal boundary here, we'll call that at y equals, let's say, we'll call it some b value, okay, because it's an unknown, then that means no matter what the function is looking like, no matter where it goes, as it approaches to the left, it'll be getting close to b. It could even be coming up and cross it, but then the n behavior still approaches that b. We could also see something like this, where it approaches that b value. So the limit as x approaches -infinity, aka left, goes towards that y value of b. The right goes towards that y value of b. All right, y'all, we'll see you next class.